Hello and welcome back. It's Jason from STEM Online Tutoring, where we make mathematical and scientific content um, for educational purposes for people who want to learn more about mathematics and physics, specifically from grades 11 all the way till end of second year undergraduate university education. So if there's any topics that you're interested in learning, whether you're a student, whether you're a person who or older student who wants to get back into school, maybe go to college or university, or you're an enthusiast, or you're an academic yourself, and you want to be able to create a course syllabus for a course that you're teaching, and you get ideas from these videos. It's for everybody. Okay. All right. So today we're going to continue with mathematics. Last 3 or 4 videos, I went into a topic called introductory logic. Okay, because I felt that it was very important to discuss not not mathematical equations or formulas per se, but more about the mathematical thinking process, which turns out to be as important, actually more important, when you get into more advanced classes, especially in university. However, today we're going to go back to calculus, but we're going to do calculus using uh, the type of rigorous mathematical thinking that I sort of exposed you to in the last 3 videos with a logical foundation. Okay. In other words, still calculus. Doesn't matter what you call it. In the math community, we call it analysis, right? Which is a way of using logical deductions for calculus. Okay. Still using all the theorems, all the other things in calculus are same, but we just do more about either proving or showing counterexamples. So today we're going to look at continuity versus differentiability. Okay, so we're going to be looking at a particular question here when it comes to continuity versus differentiability. And the question is, how do you use a counterexample, okay, to show that the converse of the following is not true? If a function is differentiable, okay, then it is continuous and therefore it is not true. Okay. I'm going to go step by step slowly, showing you how to break down this paragraph into something that is understandable. Okay. So, first thing, in order to start the question, we need to understand what the question is asking. The question is asking, right? What in reality, what it's asking is this. Okay. So, let me show you how I'm going to verify or prove this. Okay. So, for the proof here, okay, what I'm going to say is that in reality, right, because it says the converse of the following statement has to be not true. Okay, so we want to show, okay, so I'm going to write here. So uh, in in this question, okay, so it's good to sort of set up any proof by stating or restating it in a phrasing that is more mathematical and makes sense, right? We want to restate what we actually want to prove, right? It's just so that we go in a chronological and systematic order. Okay, make sure that we're understanding everything in the paragraph. So in this question, right, we are asked to prove, right? We are asked asked to right to prove, right? We're asked to prove that. Just 1 second here. We're asked to prove that, right? We're asked to prove that uh, that a function, I should say like this, actually doesn't matter, but a continuous function, a continuous 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 function, okay, a continuous function, a continuous function uh, implies that it is differentiable, that it is differentiable, okay, it is differentiable, so differentiable, okay, differentiable, and shibble, is not true, is not true, okay. I hope you understand what I mean by that, because the phrasing here, right, if I highlight here back in the question, it says if a function is differentiable, then it is continuous is not true, okay. But we're looking at the converse. What it means by converse is means we're going the other direction of the statement, right? So we're going backwards from the statement that we want to show that it's not true. So we would say that we start from here and then we go backwards. So we're saying that we want to show that a continuous function implies, right, that it is differentiable, and then we have to show that if a continuous function implies that it is differentiable, then it's not true. Okay, that's what we're asked to prove here. Okay, so now that I've stated what we want, what we're actually asked to prove here, we have to go through the process of proving it rigorously. Okay, and what I mean by that is we have to show all our steps. Okay, you can't omit anything in math. So let's go through it. All right. So the first thing is coming up with a counterexample that shows this. Okay. So here's a counterexample. So first, our counter. So first, let's put here our first, uh, our counterexample, example is first our counterexample would be let f of x, because it's a function, equal to the absolute value of x. Okay. Now at first, it can be a little daunting to come up with counterexamples for problems. However, though, it's important because it's another way of reasoning that is very important in math. Quite often you'll have a statement, and then if you want to verify if a statement is true or false, you may need to provide a legitimate counterexample that shows that it's either true or false. Okay, so depending on the problem. Now, how do I know that to choose f of x equals the absolute value of x? Well, first off, right, if we draw a graph here, okay, so I'm going to draw a picture. Okay, so let's do a diagram. If you look at the diagram, right, I have here, right, an xy plane. Okay, I have xy plane. I know that absolute value of x looks like this. Okay. This is f of x equals absolute value of x. You see notice, right? And the reason why it looks like this is because it's an absolute value function. An absolute value function, right, is the following, right? So if we put on the side here, absolute value of x is a piecewise function where you have x if x is greater than 0, right? Greater or equal to 0, and negative x if x is strictly less than 0, okay? And if we were to graph individually each function, because that's what a piecewise function is, multiple functions in the whole function. If you graph x, if x is greater or equal to 0, then we get this branch here, the right-hand branch. And when negative x, when x is less than 0, we have this, the left-hand branch, which is a line, okay? Two lines here that intersect at 0, 0. Okay? Now, one thing I want to put up here that's very important, right? That I want to clarify and make sure you understand is the fact that this function is continuous because there's no holes, there's no jumps, there's no uh, jump discontinuities or any of that stuff, right? So what I mean by that, there's no open holes, there's no discontinuities like this. This is a discontinuity, right? Okay, here the entire graph continues. There's no stopping point. There's no jumps. There's no discontinuity. So it keeps going forever. So we know that it's continuous. Okay. Now we want to show that if a function, right, is continuous, then it cannot be differentiable. Okay. And if we can find at least one counterexample that shows this, then this is true for all functions. So if we find at least one, right, at least one example that shows this, then you cannot dispute it because we found at least one example. Okay? Okay, so we know it's continuous. So how do we show if something is differentiable? Well, I'm going to write something out here. So differentiability, differentiability for differentiability. Okay. And we show differentiability if we can show that the limit, okay, if we can take the limit as h approaches 0 of f of x plus h minus f of x all over h, okay? If we can show that the left hand and right hand limits are are the same, it's going to be differentiable. If not, they're not differentiable. Okay, so taking this into consideration, differentiability is from this formula from first principles. F prime of x is equal to this. Okay, so then we need to take two limits, as I said, right? One limit as h goes to 0 from the left of f of x plus h minus f of x, compare it, okay, to its right-hand limit, right? And the limit as h goes to 0 from the right-hand side of f of x plus h minus f of x all over h as well, okay? So we need to show this. So let's go to the side here. You'll notice, right? So here is how we're going to show this. If f of x, right? So if f of x, right? So because f of x is equal to the absolute value of x, okay? Therefore, I know that f of x, right? F of x equals x, okay? This is case 1 when x has to be greater than 0, okay? This would be case 1, right? Because if I have absolute value of x, either f of x equals x when x is greater than 0, or f of x equals negative x when x is less than 0. We have to do two cases here. So we'll start off with case 1, okay? Then what we're going to do is we know we need f of x to use our differentiability formula here, okay? But we also need x plus h, this f of x plus h. Substitute f of x plus h into x. So substitute into f of x plus h and see what the expansion is. This yields x plus h, okay? So now we have f of x and f of x plus h, right? Now we're going to use our formula for the derivative, which states that f prime of x is equal to limit as h approaches 0 to the right. I'm going to explain what that is, of f of x plus h minus f of x all over h. Okay. Now, what do I mean by h approaching 0 from the right or h approaching 0 from the left? That means I have to evaluate the limit as h is approaching the graph, as h approaches 0 from the right of the graph. So if you look back at our diagram, that's why I drew it, right? This point here is at 0, 0 at the origin. As h approaches 0 from the right, that means that if I draw an arrow here, coming in like this, right? So we're going to go from the right of the graph, the very rightmost point of the graph, and once we hit that graph, we're going to intersect at 0. Okay? So with this happening, okay, that means since I'm hitting the rightmost part of the graph, I'm only hitting f of x equals x. Okay, so I know that way I'm able to determine which part of the piecewise function I'm using. Am I using f of x equals x or f of x equals negative x? Okay, let me just erase that. All right, so in this case, f of x equals x because that's the right hand part of the graph, and that's going to the right. So substitute that in. So we get f prime. So f prime of x equals limit as h goes to 0 of x plus h here minus f of x, which is x, right? All over h, okay? Over h, okay? Okay. And then after from this part here, right, what you're going to notice is that you can only cancel out something, right? Right. So you can only cancel out, well, it's very easy to figure out what you're canceling out here, right? What do you think gets canceled? Well, it's very straightforward. You're canceling out the x, right? Very simple. X gets canceled. Therefore, I get f prime of x equals limit as h approaches 0 of h over h. H and h gets eliminated now, right? Because it's h divided by h. This is limit as h goes to 0 of 1. This is equivalent to f prime of x, right? Therefore, the limit as h approaches 0 of 1 is just 1. F prime of x, right, is equal to 1. Okay, so we figured out what the right-hand limit is. Okay, now this was case 1. Case 1. Now we do case 2. Now case 2, I'm going to set up f of x equals absolute value of x. This is when we have to deal with f of x equaling to the negative branch of x where x is less than 0. Okay. So now we're going to substitute. I'm going to substitute into our guy over here, right? So it's going to be f of x plus h because that's what we need. Okay, so this now becomes negative parentheses x plus h. Okay, so that's what we have. In other words, this is equivalent to negative x minus h. Make sure you put the negative in front of the entire parentheses, otherwise it's not going to be correct, right? So this is my f of x plus h. Okay, now use the differentiability from the left-hand part, right? So we're going to use f prime of x equals limit as h goes to 0 from the left-hand side of f of x plus h minus f of x all over h. Okay. All right. Then from here, right, we're just going to continue f prime of x equals the limit as h goes to 0, right, of fx plus h, which was negative x minus h, minus f of x, that's a negative x, right, because that's what we had for the negative branch of absolute value of x was negative x, all over h. Negative x and negative x is negative 2x, so get f prime of x equals the limit as h goes to 0 of negative 2x minus h all over h. Okay. So we're almost done. You'll notice as since I'm substituting h approach to 0, put 0 everywhere. So this is going to be negative 2x. Well, I mean 0 for h only. Negative 2x minus 0, right, over 0. Now you're going to notice something problematic here, right? We get f prime of x to be undefined. Okay. Is when you approach, well, as h approaches 0, you get an undefined point in the denominator, right? Indeterminate. So this doesn't exist. Doesn't exist. And the fact that it doesn't exist, the left and right hand limit, therefore, obviously, right, it is not differentiable. So this is not differentiable. Okay, and we just proven it by this counterexample. Okay, so proved. Another way to know that the statement beforehand, without even showing a counterexample, um, is true, that anytime when you have a continuous function, it cannot be differentiable, is because there is a theorem that states that the following, right? It states that, so here's a theorem. So here's a theorem from calculus, and it states that a function f of x uh, is differentiable, is differentiable, differentiable, function of x is differentiable, then automatically this implies that it is continuous. Notice how there's only one implication here, right? So a function f is differentiable. If it's differentiable, then it is automatically it has to be continuous. What we are showing in the problem that we did, we show that a continuous function is always implies that it is it always implies that it is not differentiable. In other words, by this theorem alone, you can notice that it's not a biconditional. It only shows one hand. The function is f of x is differentiable, implies that it's continuous. It can never be the other way around, right? It cannot be also that it is continuous and it's differentiable. That is false. And the fact that this theorem only has one implication and not a biconditional automatically tells you that the statement that we were proving in the question, that our counterexample is correct. Okay. I hope you enjoyed this video. Uh, uh, if you want to stay tuned for more math and physics educational content at a higher level, please stay tuned. There'll be much more videos from calculus to logic, and also because we also do uh, physics videos as well, so there'll also be topics in that area. Also, don't forget to like and subscribe, and if you can leave comments in the YouTube video, that'd be great. What you would like, what type of videos you may want me to, what other videos you want me to do on topics you find difficult or anything else. That'll be handy for me. Have a great evening. Bye bye.